uh, it's impossible for both cows, like one of the cows must fulfill this first condition, containing all cows of its type, as the two cows also cannot contain each other because one cow must be ahead. We notice that so if the ranges look like this, in order for like one cow to contain each other, there must be one that's ahead and that can't be covered by the other since all cows can only cover cows that are behind them. So this means that one cow must have condition one satisfied. Have condition one satisfied. And what this means is that it must also fulfill this, being it must be the first cow of its type. So what this narrows down the problem to is that we can just choose one cow. We choose, like, for example, either G or H. We choose it to be the first cow to be the leader. If the first cow contains all cows of its type, that means that it can possibly be a leader. And then all we need to do is just choose cows from the second one that contain it. And this can be done really quickly. This can be done just by looping over all the cows and like all the cows ahead of it. So I'll write it here. Let me just find some space. If we put all the cows, so choose one cow that is first in its type to possibly be a leader. Now, the other cow can either satisfy the first or the second condition. So if it satisfies the other condition, all it needs to do is cover the current cow. So if we just choose the current cow here, like if it's a list of cows, we choose the current cow to be like in this position, then all we need to do is check the cows in the positions ahead of it and see if the range of the cows like extends past the current one. And then if it does, then it will satisfy the second condition. Otherwise, and we can just do this for either type, since we know that like one of the cows must satisfy the first condition. There's only two cows that can like satisfy the first condition. And that means the total time complexity here would just be 2 times n. Since after we choose the cow to satisfy the first condition, all we have to do is check the cows ahead of it and then see if they cover the other cows. Does this problem make sense to everyone? Okay, I don't repeat like the final solution. Okay, so repeating the final solution, we can see that the key observation to make is that in order to contain all the cows, it must be the first cow of its type. And this is apparent because a cow can't go like the range the cow covers is always behind the cow. So if there's a cow it's missing ahead of it, there's no way for it to cover it, so it can't contain all cows of its type. So that means there's only 2 possible cows satisfying this, one for each type. There's only 1 possible cow for each type, and then that means it's 2 total. And that means that in order, and the other observation we can make is that like at least one of the 2 leaders we choose must have this condition satisfied, because otherwise like 2 cows can't cover each other. So that means that they can't both be leaders that only contain the other cow's leader, since I've already shown that they can't cover each other. Means that one of them must be a leader because it contains all cows of its type. And this means that there's only 2 options for this, so we can just like loop over the 2 possible options we have. And once we choose the option of like the first cow of its type, we check if it actually does cover all of the cows, like in its range I to E of I. If it doesn't, then that means like this cow can't be a leader, and that like we can just kind of throw out this case and we move on to the next one. But assuming it does cover all cows like from I to EI of its type, then that means that all I have to do is check the other cow must be in the like positions ahead of it in order to contain this cow. So that means that we only need to check the cows ahead of it, which at most can be n cows, and it will like the solution will be finished here. Well, the time complexity here would be in fact O of n, because there's only 2 cases for the the first leader that contains all cows of its type, because as we've shown, there's only 2 possible cows, and then n because we have to check the cows ahead, ahead of it to see if it contains this cow, and it can be the other leader. Okay. So let's just go on to the next problem then. If no one else has any more questions. Estimate the cutoff score to the silver level. I'll do that after I finish explaining all three problems. I'll get to it. So now problem 2. Again, I'll just do a brief summary of the question. So there's going to be n cows, n less than or equal to 20. And they're numbered, and they're like occupy a row of stalls numbered from 1 to 100. And like cow I occupies like some range. It's like a continuous range, and it requires the temperature to be dropped to at least CI units. To be CI. And then there's also M air conditioners. M less than equal to 10. And then it costs MI money to run each conditioner. And it cools a range of stalls by P of I. And then we just need to find, it also costs some amount of money to run, and we want to minimize the amount of money total to cool all the cows to the required amounts. Okay. Some money to run. Find min cost. All right, let's begin this problem. So when we first look at this problem, we can see that like the first things we can notice is that M and N are actually extremely small. M is small enough to the point where we can basically do honestly whatever we want to it. We can even make it like exponential. Like honestly, yeah, like it doesn't really like the time complexity is basically like as long as we like do like keep it within like reason, not like M to like the power of M or something. Like as long as we like keep it like somewhat reasonable, basically everything will pass as M is tiny. So that means that all we need to do is basically just think of some solution that could possibly work. So the first solution we can think of is like, what if we just try like the problem asks us to find like which air conditioners we want to turn on or not. So then let's just try all possible combinations of turning air conditioners on or not. Right. Like that, that's just basically doing exactly what the problem tells us. Right. Like the problem wants us to find some subset of air conditioners turn on. Let's just try every single possible subset. So this brings us to the idea of like bitmasks. So I think some of you guys might have heard of it, but it's just basically using binary numbers to brute forcefully try every single combination of like on or off of some number of like variables. So try every combination of air conditioners turning on or off. So how it does this is basically, as like I assume most of you guys know, every number can be represented as a binary number. So for example, like the number 4, right, can be represented as 1, 0, 0. Number 5 will be like, actually, no, like 7 or something will be represented 1, 1, 1. So what we can do here is that since we want to like just brute force over turning on or off number of M numbers, we can like represent each air conditioner by like a single binary digit. So if you have a 10-digit binary number, then that means that like every 10-digit binary number will correspond to some like combination of these air conditioners being either on or off. So I just take like some random binary number like 1, 2, 3, 4, 6, 7, 8, 9, 10. Okay, so what this binary number would represent is saying first air conditioner, because we notice that it's a 1, we turn it on. Second one, because it's 0, we turn it off. This one is on, and then so on. They're all 10 digits. And then basically we are able to very efficiently like run through every single one of the combinations by just like looping some number through like 0 to 2 to the m. So what this does is this gives us all of these like 2 to the m binary numbers with like digit length m. So like let's just take like a shorter amount. Let's say like m equals 2. Then actually m equals 2 is a little too small. Let's just like m equals 3. So if there's 3 numbers, and like in terms of binary, it'll be 0, 0, 0 for like 0. And then 1 would be 0, 0, 1. 2 would be 0, 1, 0. 3 would be 0, 1, 1, and so on. And every single one of these will correspond to a combination of like air conditioners being on or off. So for example, this one will correspond to all air conditioners being off. This one will correspond to all air conditioners, like only the first air conditioner being on. This one will be the second one being on, and this one will be the first and the second one being on, and so on. So all we have to do is, and like because of the way binary works, binary will cover every single number that could possibly exist with this many digits, because we're basically just counting up one by one. So every single number would be included in this like range as we traverse it. So that means that all I have to do is just loop some number through 0 to 2 to the m. And for each, we just check, each one represents a combination. We try turning like the air conditioner specified by this combination on or off. And then we just have to see how much, if this air conditioner combination satisfies the condition, and if so, like if it's cheaper than the current cheapest solution. And all I have to do is just see by the end of this, we'll just be able to find the cheapest combination, the cheapest solution, as this brute force will actually cover every single combination. So for each combination, it's not too hard specifying whether or not each combination, it's not too hard to specify, like checking whether or not it satisfies. All I have to do is like by turning this air conditioner on, we're just changing everything in this range. We can honestly just do this by brute force since the range is pretty small as well, just 1 to 100. So like cool. Does it sound more intuitive to DOS the solution along the lines of stalls? I mean, I personally believe that like I think like because like Bitmasks is basically just doing the problem like when we consider the problem, it's just trying every combination of like either turning on or turning off this air conditioner. So I think like this is probably the most intuitive solution. Like we just try every single combination of turning on or off the air conditioners. That's basically what the problem just wants us to do. Yeah. And we notice that M is really small. When we notice that M is very small, this immediately like kind of alerts us to the fact that like we are in fact able to do 2 to the power of M. There's like a lot of things that open up when we notice that M is very tiny. So cool these stalls specified by each conditioner. And then we can just loop over this in 100 and like just loop over this, just brute force. And then we again and after this, we can just check for each cow if the position specified is cool to the acceptable amount. And overall, that's just another loop over, which will take n times 100 times. So overall, the time complexity of this is going to be, let me just erase some stuff to the side. So time complexity. So it's first 2 to the power of m, because we're looping over, it takes 2 to the power of m to loop over every single combination of the air conditioners being on or off. And then checking like cooling the stalls to this like intended amount by each air conditioner that's on will take 100, because the stalls are numbered from 1 to 100. So it's 2 to the m times 100. And then afterwards, we need to check whether or not for each cow, their range is cool to an acceptable amount. So this will be 2 to the m again for each combination. I should probably just do it in parentheses. Afterwards, it will just be n times 100 again. Because for each cal, we'll just brute force over it, loop over the range, and see if everything in the range is cool to the acceptable amount. So overall, if we just throw out the constant, it's not the constant, it would just be 2 to the m times 100 times m plus 1 by just grouping them together, which is basically just 2 to the m times 100 times 20, which will pass an acceptable amount of time because times n, I mean, times, which will pass an acceptable amount of time because it's 2 to the 10th times 100 times 20, which comes out to around 2 to the 10th is around 1,000. So it's 1,000. It comes around 2 million. Just 1,000 times 100 times 20 equals 2 million, which is an acceptable amount of time. About the question in the chat, DFS the solution. I didn't even really think about that solution. I think Bitmask, yeah, is in fact a more intuitive one because it's just straight up the brute force solution to do it. Like if you were to do this by yourself, you can just try every single combination. Yeah. Does anyone have any questions about this problem? DFS worked because, okay, if you guys, all right, if there's no questions about this solution, then I will be going on to the next one. So the next solution, I will quickly first be going over the problem statement again. There is going to be Q strings consisting Q less than or equal to 100, strings consisting only of M's and zeros and O's, I mean. So basically, it's like almost like moves, basically, fitting with the theme of USACO. Each string is going to be, I think, at most 100 characters. All right, so for each string, there's going to be 2 operations. So operation 1, replace, like we'll just change, I'll just say change. So change either the first or last character. Or last character. And then the second one will be remove first or last character. And then the problem asks for each string, find minimum number of operations to turn the string into moo. So what we can, an immediate observation we can make is like, well, let's just go to the subtask first. So if we are able to, first subtask, whenever we see a new problem, if we don't immediately see a solution, let's just try going on to the subtasks. So subtask 1 is every string has length at most 3. Well, we can clearly see that if the string is less than 3, if it's like either 1 or 2, then like there's no possible way to get moo since there's no operation to add a character, and since moo is 3 characters long, like there's no way something of length 2 can turn into something of length 3 because there's no operation to do it. So if length less than 3, impossible. And then so that leaves us for the first subtask of length equals 3. So if the length is equal to 3, well, there's a lot of ways we can approach this problem. First of all, if we can see that, well, just going from like the sample text, like the sample input, we can see that if there's an M in the middle, there's no possible way for us to change this M to an O without removing some characters, right? So like in the sample, we have MMO, and then this was deemed impossible because there's no operation to like change something in the middle. In order to do it, like we have to remove some character, change this, but then there's no way to add it back. So if length is equal to 3, we can quickly come to the conclusion that if like character in the middle is M, impossible. Otherwise, it's just checking if the middle character is O, it's just checking the first and the first character and the third character and seeing like how much, like if we needed to change this or not. And it depends on just like if we need to change it. And it's just one operation for each change. If middle is O, then just see how many operations to change the first and this like last one. How to change first or third. All right, for example, if it's like OOM, then we need to change both the first and the last one. So it'd be 2 operations. But if it's like MOM, then we only need to change the last one. So it'll only be 1. Or it's not, yeah, it's not too difficult. We can like quickly just see it just from intuition. Overall, like there's also just not many cases. So if you're like to like not make this observation that the character must be M, we can also just brute force. There's only a total of 8 possible of like, 2 to the power of 3 equals 8. There's only a total possible of 8 possible substrings of length 3. So if you want to just like have a bunch of if statements checking every single combination and like printing it out after doing it by hand, that's also doable. Okay. So overall, this subtask shouldn't be too hard. And then we can see how, and next we'll see how we can maybe expand this subtask to solve the whole problem. Okay, so full solution. So building off the subtask, I guess like the key observation we need to make for the full solution is that we can see that there is no way to like modify something in the middle. And like the problem just ends up being like if length is greater than 3, then we're gonna have to remove some like amounts of characters either at the beginning and the end, and it will just leave us with until we get some substring of length 3 remaining. Now, if we have this like long string in the beginning, we'll eventually just have to like cut off. We can't remove anything in the middle, but we'll just have to cut off something from the beginning, something from the end, until eventually we're left with something with length 3. That's the only way we can possibly get a substring with length 3, and like we need a substring with length 3 in order to get the final solution of like MLO. So this means that we can notice that the final answer is going to be originally a part of the substring of a length 3 substring of the original string. So final string going to be the length 3 substring of original. Like it can't be like 3 things pieced together, right? It can't be like one character here, one character here, one character here. Because just if we're keeping this, there's no way to remove the things in the middle. That means that it must have been a continuous length 3 interval from the original string. So now if we know that it's going to be a continuous length 3 interval, and we also know that we're going to have to like remove so many, like we're gonna have to like run operation 2 just original length minus 3 number of times. All this is that we just have to choose which length 3 substring we want to keep and like incorporate into our final answer. So we can just finish this off with a brute force on which length 3 substring we want to keep. We already did this in like problem in the first subtask. We can quickly find the answer for any substring of length 3. And that means that all we have to do is just find which substring of the original one, which length 3 substring would have been the fastest to process with if like all the other characters were already deleted, which we can treat them as they are, as we aren't going to use them at all. Which substring will be will be will be chosen as the final. Choose the one with least number of operations. Least operations. Okay. Does this make sense to everyone? If anyone has questions about this problem, just ask in the chat. Okay, I assume that no one has questions, and then let's just go into I guess someone else asked earlier, what was my prediction on the passing score. I think compared to December, this contest was easier in my opinion. Problem 1 was probably the hardest because it required some observations, but even then it was kind of, I think the first 2 subtasks of problem 1 were at least pretty easy to get. So that should be at least half credit. Problem 2 was kind of, it was a little bit tricky, I guess, but it was just you need to know the Bitmasks. If you knew Bitmasks, this problem was trivial. But if you didn't know Bitmasks, I think the problem would have been kind of hard to approach because there's no real way to I think some people were talking about DFS in the chat. I think there might have been a DFS solution as well, but I haven't thought too much about it. So I think problem 2, it's just, yeah, if you knew Bitmasks, problem was pretty easy. And problem 3, I think the problem is pretty straightforward. You just go on the first subtask, and after you do the first subtask, you can just notice that this observation wasn't incredibly difficult to make. I think the passing score would probably be 750 or 800 for this contest, but I'm not exactly sure. Overall, I think that basically just wraps up our tutorial session for today. Teacher Guo, can you bring us the next slide, maybe? Oh, I think someone asked in chat, how do you generate the binary numbers for Bitmasks? You can just loop, since we need to consider every single possible combination, we can just loop the numbers from 0 to 2 to the m, since we need to process them all anyways. And it doesn't matter what order we process all the numbers. So we can just process them in any order. And the easiest way for us to do it is just by going from the it's just looping over all of the possible numbers. Since this that'll just basically be one for loop from 0 to 2 to the m. Number 2, I guess apparently a lot of people had problems with number 2. Yeah, I think number 2 is just, if you knew Bitmasks, the problem becomes really straightforward, but otherwise there are probably a bunch of other solutions to do it with prefix sums, maybe trying out different combinations, maybe DP or something, but yeah, there would be other issues. Okay. Wait, Teacher Guo, are you going to be screen sharing the slides?
Yes, let me share the slides. You can introduce what's next for the students here.
Okay. So next, onto ideas how to prepare for this next, for the next USACO and how this contest will influence us. So I guess for next USACO, this contest kind of thought that even in bronze, some knowledge is actually needed. Because some algorithmic or data structure knowledge is kind of needed, especially number 2. Basically, if you knew Bitmasks, the problem turned really easy. If you didn't know Bitmasks, the problem was actually kind of difficult. Yeah, so this kind of goes to show that even for bronze, it's probably better to take some classes. All of these information would be covered in XCAM's classes. So currently, the XCAM 2023 Spring Enhancement class for tailored contest experience is open to enroll. There's a total of 9 sessions. This will give you basically 9 simulated contests representing USACO contests, and it will give you a very good idea of how to approach the problems in the future. As well as this, XCAM 2023 Summer Camp from June 17th to June 28th is also going to be open. There will be bronze to platinum camps. There's limited spots, only 20 per level, so I recommend you try to sign up as early as possible for these. XCAM weekly class for building up your knowledge foundations. it will just be for the spring semester. From the quarter starts from April 1st. There'll be 9 weeks in total, and yeah, overall, it's just weekly classes with teachers. They'll be assigned problems. They'll like be able to help you during the week, and it's just overall a really good like learning experience, especially if you want to learn new algorithms. This like the weekly classes is what teaches you most of your new algorithms, as we've shown. Like you might want even like for bronze, learning these new algorithm data structures such as bitmasks is pretty important. As well as this, there's going to be public monthly USACO mock tests for bronze, silver, gold, and platinum. Stay tuned by submitting to this link on the slides, and instructions will be emailed to you if you submit this link.
Thank you. Thank you, Alex.
No problem. I will be passing on to teacher Guo.
Okay.
Thank you guys for attending.
Thank you.
Bye.
Thank you very much. Yes. Yeah. Okay. That's ending is our bronze solution session. Let me stop the sharing here. Stop the recording here. So next, we use the same Zoom for the silver. Hey, Edward, are you there?
Yes, hello.
Okay, let me 1 second. Let me start the recording and broadcast. Give me 1 second. Yes. So, bronze students, if you want to continue listening to the silver, you're welcome to stay. I think some of the silver students just joined. Let's wait maybe 1 more minute to have more time get the students in the room. Let me start the recording here.